Welcome. So, we will discuss the solutions of the first week assignment today. Now, before that I would like to tell you a couple of things. That is, you might be able to receive or download a PDF file of this first week lectures. One caution from my side that those downloaded version what you will see is not textbook. So, that is the verbatim whatever I am speaking or I was speaking, that has been recorded. So, sentences as you read in the textbook, it will not be like that. So, best thing is to watch the video repeatedly, and wherever you had some doubt that words have not come properly, sound you could not hear properly, go to that downloaded PDF file and check there. Of course, equations and all these things whatever is shown in the video are exactly appearing there. So, nothing extra is appearing. It is only to remove some of the doubts which you could not hear properly. So, watching the video will help you understand much more. And also another thing is that there are some slip of tongue type of mistakes occurred, like in the Inmarsat satellite in the first lecture. The Inmarsat satellite weight, though it was projected properly more than 6,000 kg, I simply said 6 kg instead of 6 tons. So, those type of slip of tongues might be there. Don't worry about that, look at the video properly and you will get the correct things. One more things I will try to mention, that is, you might have observed that two terms I am using interchangeably, that is rotation and revolution. If you go by right definition, whatever I said, they are completely interchanged, many times they are interchanged. It is shown in video as well as spoken. I think you understand what I try to mean there. Understanding is important. So, now let us go to this assignment, and those are very simple assignments. If you watch the video carefully, you can do it yourself, but still I will try to show you, I will try to point out, so that you know you will be able to solve it much faster. I just remind you. Let us look at the assignment question number 1, which says determine the rise in antenna noise temperature, that is delta T, during sun conjunction for 3 gigahertz receiver with antenna efficiency of 60% and beam width of 4 degree. Now, and there are 4 options given, you have to find out which is the correct option. Also, one thing you try to remember on all these things, most of these questions, that the options which are given and what you calculate through the calculator, it may not be exactly same based on your calculation. Like some people take pi value as 3.14 for their calculation. If you take the pi as it is in the calculator, there will be different number appearing, because after decimal 0.14 there are many more decimals are there, and since we are dealing with very large number, so the results may vary. You have to select the nearest option which is most suited. So, with this let us try to take a look at this problem and solve it. Try to recollect what was the sun conjunction. Sun conjunction is that you have the earth, and let us say the sun rays are coming from this side, and this is the equatorial plane, and your satellite is here, and earth station is looking at the satellite, and behind the earth station is a big sun which is radiating. So, most of this noise coming from the sun is appearing along with the signal from this satellite that is coming to this. So, this noise is increasing the noise temperature. The term noise temperature we will see much later, but right now you assume that we will be talking about some temperature which is equivalent to increase in noise. And there was a model given there in the video, if you see, that is the increase in noise temperature delta T is equal to a polarization factor P, the efficiency of the antenna, the temperature of the sun, and equivalent sun disk square. And since from the sun the polarization of the electromagnetic wave which is coming here is random, and your antenna may have a fixed polarization. So, P value is taken as 0.5. The value of antenna efficiency is already mentioned 60%, that is 0.6. The temperature of the sun was given with a model that Ts is equal to 0.12 into 10 to the power 6 into F, which should be in gigahertz, to the power minus 0.75 into equivalent sun disk square. Now, this F is given as 3 gigahertz. Sorry, d square will not appear in Ts, d square is already there. So, this is equal this much Kelvin. Now, that is equal to 0.12 into 10 to the power 6 into 3 into 3 to the power 0.7 minus 0.75 Kelvin, which is equal to, you calculate, it will come to 52642.97 Kelvin, and the D is mentioned as is equal to 0.48 by theta, when theta, which is the antenna beam width, is greater than 0.48 degree. In this case, theta is given as 4 degree. So, we will take equivalent sun disk as 0.48 by 4 degree, that is equal to 0.12. Now, if you put all these values there, then your delta T will come out to be 0.5 into 0.6 into 52642.97 into 0.12 square, which if you do the calculation, it will come out to be 227.4 K, and our options were 2.274 K, 22.74 K, 227.4 K and 22274 K. So, it looks like that option C is the correct option. So, the correct option is option C in this case. In this particular problem, you have to simply remember this particular model and corresponding equivalent values like Ts, how it is to be calculated, D, how it is to be calculated. Eta and P is normally taken as 0.5, eta will be given. Okay. So, let us go to the next problem. The next question is related to the ellipse and sun as a earth as a focus of the ellipse. A satellite is orbiting in an elliptical orbit with apogee height at 20,000 kilometer and perigee height at 400 kilometer. Remember these words, height, that means it is from the surface of the earth. So, the apogee distance and perigee distance to be calculated, height plus the radius of the earth. Normally in my class I mentioned that we take a model that earth as a sphere and the radius of the sphere is 6,378 kilometer. unless it is specified it is slightly different. So, we will take those numbers. And with this elliptical orbit, the ratio of the velocity at perigee to that of apogee, velocity of the perigee to that of apogee will be, these are certain numbers given, different options given. You have to calculate and find out which option is correct. So, let us try to see how do we calculate that. First, let us see the apogee height is given. So, the apogee distance, if I call R A, is apogee height is given as 20,000 kilometer plus 6378, that is 26378 kilometer. Similarly, perigee distance is, the perigee height is given as 400 kilometer plus 6378, that will become 6778 kilometer. If you know apogee distance and perigee distance, we can find out the semi major axis A as R A plus R P by 2, which will come out to be 16578 kilometer. And if we know the semi major axis and the apogee and perigee distances, then the velocity at apogee is, velocity square is given as a constant mu 2 by, it is apogee velocity. So, 2 by R A minus 1 by A, it is V A square. Similarly, V P square, which is velocity at perigee, will be mu 2 by R P minus 1 by A. Now, what is asked is the ratio of the velocity of perigee to apogee. So, we can do it this way, V P square by V A square is, mu will get cancelled. So, it will be 2 by R P minus 1 by A divided by 2 by R A minus 1 by A, and V P by V A will be root over of that, V P by V A will be square root of 2 by R P minus 1 by A divided by 2 by R A minus 1 by A to the power half, that is root over of that. So, if you calculate, it will come out to be a number as 3.89, and our options which were given 3.89, 7.07, 15.15, 2.56. So, looks like option A is the correct option. So, option A is the correct option. It is ratio of velocity. So, there is no unit. Let us take the third problem. A satellite is orbiting in a circular orbit, which is 1000 kilometer away from the surface of the earth. That means, orbit height is given and it is a circular orbit. Then how many times in a day the satellite will be overhead from a particular location on the earth? Let us assume that orbit is such that it is going overhead from the observer. So, it is a circular orbit, and the duration of the orbit if you can find out, then we can also find out in a day how many times the duration of one orbit is completed. So, that will be times that can be calculated this way. And since it is a circular orbit, the equations are very simple, that is the duration of one orbit is 4 pi square r cube. This r is the radius of the orbit by mu. This is to the power half 1 by 2. Now, r is the radius and it is 1000 kilometer height. So, 1000 plus radius of the earth, as I said 6378 in general we take. So, it will be 7378 kilometer. R is known and the mu value is a constant. We already know that, you have to always remember that 3.986 into 10 to the power 5 kilometer cube by second square. So, if you put these values, the T will come out to be a number like 6306.9472, like that many numbers will come after decimal second. And how many times a day? In this case, assume that normal solar day. So, number of times orbit number of times the satellite will orbit over a solar day is one solar day in terms of second is 86400 second divided by 6306.94 etc. If you put, you will get a number like 13.69 dot 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 like that. So, complete pass over the overhead is 13 times it will complete, and it is more than 13 and a half times. The second time it has not, next time it has not come overhead. So, your answer would be 13, and options which were given is 16, 15, 14, 13. So, option D is the correct answer. So, it will be option D. These are all simple calculations and based on the formula if you remember. But then let us look at another much earlier. Initially we have talked about, you know, this problem is so simple. It says a satellite is orbiting in an elliptical orbit. Thus, a generic conclusion can be drawn as the velocity at apogee is greater than that of perigee, the velocity of apogee is less than that of perigee, velocity at apogee is minimum, velocity at apogee is maximum. So, these type of 4 different options are there. I hope you know the answer, but then let me just explain, try to explain. You try to remember the Kepler's second law, which states that the area swept will be by equal time. So, near the apogee, this is apogee and this is perigee. So, here it will go faster, here it will go slower. So, the answer is already known, but it can be shown also differently, that is the apogee distance R A is always greater than perigee distance, and the velocity at apogee is 2 by R A minus 1 by semi major axis square root. Velocity at perigee is 2 by R P minus 1 by A square root, and since R A is larger than R P and R A is in the denominator, the velocity at apogee will be lower than that of velocity at perigee. Velocity of apogee will be lower than velocity at perigee. And our options which were given were B options say that the velocity at apogee is less than that of perigee. So, B option is correct. So, it will be option B. Let us see the fifth problem. This was also very simple, again using the similar formula. Determine the orbital height, mark this word height in kilometer, of a satellite orbiting in circular orbit with orbital period of a sidereal day. It will be geostationary satellite. Now, let us see, options are 42164 kilometer, 36712 kilometer, 42379 kilometer, 35786 kilometer, 4 options are given. Though we know the answer, but let us calculate. Let us calculate and see. I think this calculation you have already done, but there is a catch here. It says height. Now, we know in a circular orbit the radius of the orbit is equal to the time period of the orbit square mu by 4 pi square, that was r cube. So, it will be 1/3 when we go for r, and we know the sidereal day timing, that is t is 86164 second, and mu value is 3.986 into 10 to the power 5 kilometer cube per second square, 4 pi square. Here this you can see we have to use the pi value directly instead of 3.14 square, because we are dealing with larger number, and this 1/3 to the power 1/3. So, you will get a number 42164 point something 12 kilometer, let us say, depending on your calculator what you are using. But this is r, the question was height. So, height means this is earth and this is the orbit, what you got is this distance r. So, height will be this distance minus the radius of the earth. So, height is equal to 42164 minus radius of the earth, which generally takes 6378 kilometer, and that comes out to be 35786 kilometer. And let us see, the answer options were 42164. If it was from the radius full radius, that is center of the earth, this would have been the correct, but since the height is asked, 35786 is the correct answer. So, it is option D. Okay. Let us see the next question, which is question number 6. This is also related to ellipse, and added is the concept that earth is at the focus with some radius. Let us read this question. The difference between the farthest and the closest point in a satellite's elliptical orbit from the surface of the earth is 30,000 kilometer, and the sum of the distances from the surface of the earth, closest and farthest point, is 50,000 kilometer. If the mean radius of the earth is considered to be 6400, in this case is given some number which is not 6378, generally we take it, it says 6400 kilometer. Determine the eccentricity and length of the semi-major axis of the orbit. It is a problem of a ellipse. So, let us try to solve this problem. Let us take the r e, which is the radius of the earth, as which is given as 6400 kilometer. So, the distance from the farthest point is apogee distance minus this radius of the earth, and difference with the nearest points, that is perigee distance minus the radius of the earth. If we do this, this distance is given as 30,000 kilometer. This 2 RE, radius of the earth, gets cancelled. So, it is R A minus R P is 30,000 kilometer. The other one is R A plus R A minus R E plus R P minus R A, this plus, it is given as 50,000 kilometer. So, in this case R A plus R P will be 2 REs minus 2 RE, that will go that side. So, it is 50,000 plus 2 RE, which is 50,000 plus 2 times 6400, that will become 62800 kilometer. So, now we have R A minus R P and R A plus R P, and we were asked to find out the eccentricity. So, eccentricity can be easily calculated, that is E is R A minus R P by R A plus R P, that is equal to your 30,000 by 62800, which will come out to be 0.478, or nearest value is 0.48. And the other question was semi major axis, that is R A plus R P by 2, that is R A plus R P by 2, that is A, semi major axis. R A plus R P is already known, 62800 divided by 2. So, that will be 31400 kilometer. Now, this option here, it was written wrongly in your assignment, it is 31400 already written. So, the eccentricity is point here also, sorry, 31400 it will appear here. There is something wrong. There is something wrong. We will come back to this assignment clearly, which option is correct. If we will do, I will ask somebody to quickly check the check with the calculator these numbers, check with the calculator these numbers and come to the correct option. So, in the meantime, let us go to the question 7. A satellite is in a circular orbit, circular equatorial orbit, with a period of 24 hours exactly. Determine the rate of drift of subsatellite point around the equator in degrees per solar day. This is a very simple problem. That is, the given orbit period is a solar day, that is 24 hours, and Earth's rotation is less than 24 hours, that is a sidereal day, which is 23 hours 56 minutes 4 seconds, etc. This comes out to be 86400 second, and this comes out to be 86164 second. Now, it says this, the satellite is at 24 hours exactly. So, Earth is rotating from east to west, west to east, and satellite is also rotating in west to east, but much slower than Earth rotation speed. So, Earth is rotating from west to east and satellite is also rotating, but it is going slowly. So, for a observer on the Earth, the satellite sub-satellite point will be drifting towards the west. Let us say this is Earth, this is west, this is east, and this is the satellite orbit. This is going faster and this is going slower. So, for an observer who is moving away, the sub-satellite point will be drifting this side, because it is going slowly, it is drifting this side with respect to the observer. So, it is drifting towards the west. But how much? That is the fraction of this difference of the orbital period and per day. So, that fraction is 360 degree and 86400 minus 86164 and per day, in this case per solar day, that is already mentioned 86400 and that many degree 360 degree. So, it comes out to be 0.983 degree per solar day. So, it is going drifting towards the west with this much, and the answer options are given as 0.5 degree no, 0.5 degree no, 0.98 degree, we got 0.98 degree towards the west and towards the east. So, option C seems to be the correct option. See here, the correct option is option C. And okay, this is going here. So, question number 8. Now, this is the visibility. Determine the visibility arc on Earth equator from the satellite located at 87 degree east in the geostationary orbit. And there are options given as that arc is longitude is 5.7 degree east to 168.3 degree east, 87 degree east to 168.3 degree east, 163.3 west to 8.7 degree west, or it cannot be determined, something like that. It's very simple problem. If you remember that visibility we have calculated with this type of diagram, that there is a Earth station here and just grazing the Earth surface a satellite is available here, and let us call this is called the Earth station, this is satellite, and this is the center of the Earth, this is the radius of the Earth, and this is the sub-satellite point Z. Since it is grazing this, so from the satellite I can see the Earth up to this longitude and this side also up to this longitude will come. So, one part of the triangle, one sided triangle, if you can solve, we can see the other side also. And this Z, since it is a geostationary satellite, Z is a sub-satellite point which has a longitude. Now, if you remember that this was gamma. So, if I know gamma, I can find out from this longitude to up to what distance satellite is seeing the arc edge of the Earth. So, from this longitude I can subtract the gamma this side and add the gamma this side, depending on which whether you are in the east longitude or west longitude, etc. we can find out. So, we have to determine the gamma. Now, this is the distance from the center of the Earth to the satellite, and for geostationary satellite it is distance is already calculated, normally we know it, 42164 kilometer. Radius of the earth is 6378 kilometer, and this is a right angle triangle. So, cos of gamma is equal to R E by R S is 6378 by 42164 is equal to 0.1514, and you can calculate the gamma comes out to be 81.3 degree. That we have done in the class. So, what if I know Z 81.3 degree this side, I can satellite can see the arc, and 81.3 degree this side satellite can see the arc. So, this is the visibility arc of the satellite, sorry, this is the visibility arc of the satellite. Now, what is given is that satellite is located at 87.87 degree east, that is your sub-satellite point Z is 87 degree east. So, 87 degree minus east minus 81.3 degree, which comes out to be 5.3 degree east, and 87 degree east plus 81.3 degree, which comes out to be 168.3 degree east. So, this is the range we can the satellite can see, and the options where the A option itself says 5.7 degree east to 168.3 degree east, and it matches. So, the answer is option A. The end. So, we will take the assignment number 9. A satellite is moving in an elliptical orbit with semi major axis equal to 24571 kilometer. If the perigee distance is 6978 kilometer, find the apogee height and the orbit eccentricity. Again it is related to a ellipse type of problem. The remember this is apogee height and orbit eccentricity. So, let us do the calculation. Let us move this one. Oh. So, semi major axis A is given is 24571 kilometer, and the apogee is given as RP 6978 perigee is given 6978 kilometer, 6978 kilometer. So, A is R A plus R P by 2, and from this you can find out R A as 42164 kilometer. It is just R A is equal to 2 into A minus R P, you can get this value 42164 kilometer. So, what is the apogee height? Height is from the surface of the earth. So, this should be 42164 minus the 6378 radius of the earth, which is 35786 kilometer. And we were asked what is the eccentricity. So, eccentricity can be found out as E is equal to R A minus R P by 2 A, and R P value is known, R A value is known, and A value is known. So, it comes out to be 0.72, and the options which is matching is 35786 and 0.72, 35786 kilometer and 0.72, option C is the correct answer. These are all ellipse problems. Option C is the correct answer. Let us go to the problem number 10. This is a slightly elaborate calculation. Already I told you during the class, it is find out the look angle and the distance. That is an earth station at IIT Kharagpur campus, which latitude longitudes are 22° north, 87° east, is pointing towards the INSAT satellite located at 93° east. So, it is a geostationary satellite, its only longitude is given, latitude is 0. Select the correct option for the earth station's elevation, azimuth and distance from the distance of the satellite from the earth station. And already these numbers are given. Assume the radius of the spherical earth is 6378 and orbital height of the INSAT is 35786. So, the height is given, radius of the earth is given, and the options, various options of elevation, azimuth and distances are given. We will try to find out which option is the correct. This is a straightforward calculation. If you remember, latitude longitude both starts with L. So, we said that we will call capital L as latitude. So, latitude and small e for earth station, which is given as 22° north, latitude of the earth station, and longitude we said small l, and small l of earth station, that is longitude of the earth station was 87° east. And similarly, for the satellite, subscript will be S. The latitude of the satellite for geostationary satellite, it should be 0, and longitude of the satellite is 93° east. This is given, and also given R E is equal to 6378 and H is equal to 35786 kilometer. So, to find out all these things, first we have to find out gamma, and if you remember, cos gamma is equal to cos of L E cos of L S sin cos of small l s minus L E. It is immaterial, L E minus L S, because it is cos, and L S is 0. So, using this difference of longitude and cosine of that and cosine of the latitude of the station, you can find out gamma is equal to 0.9221, something like that, and correspondingly gamma can be found out using cos inverse as 22.7643, so many after decimal places degree. Now, R S, that is from the center of the earth, the distance of the satellite is earth radius plus the height, which is given 35786. So, that is 42164 kilometer. Now, the distance, if you remember, is R E square plus R S square minus 2 R E R S cos of gamma and square root of that, which approximately will come out to be 36367 kilometer, approximately, some fraction number will be coming. And the elevation is cos inverse of R S sin gamma by d. If you put these values of d, R S and gamma, sin of gamma, you will get a elevation number as 63°.345 degree. Now, we have got elevation and we have got d. For azimuth, if you remember, we had to calculate an intermediate angle, which is alpha, which is supposed to be tan inverse of tan of difference of the longitude Ls minus Le divided by sine of Le, which you will calculate, you will find out 15.672 degree, that is alpha. Now, for the azimuth, we have to find out where is the earth station. So, for azimuth we said that if earth station is in northern hemisphere, and obviously the earth station is at IIT Kharagpur, which has a latitude of 22 degree north. So, earth station is in northern hemisphere. If so, and then if the sub-satellite point is east of earth station, sub-satellite point is 93 degree east and earth station longitude is 87 degree. So, it is east of earth station. So, if SSP is east of earth station, then azimuth is 180 minus alpha. Since alpha we have found out, alpha is 15.672 degree. So, the azimuth is 180 minus 15.672 degree. This after decimal many things can be done. So, it comes out to be 164.32. And let us look at the option. Option wise we got azimuth 164.33 nearest, distance we got 36367 in one of the option, same option distance is 36367, and elevation we got 63.34 degree, elevation we got 63.34 degree. So, this option A seems to be correct. So, the answer is option A. Okay. Now, we go to the assignment number 11. This is a satellite in circular orbit with 1000 kilometer orbital height, transmits at 2.65 gigahertz. A station in the plane of the satellite orbit receives the signal from the satellite when it is rising from the horizon, Since it is a low Earth orbit satellite and it has a good velocity and it is rising from the horizon. So, the frequency what it is transmitting will be received with a Doppler shift. So, the Doppler shift of the received signal you have to find out will be in the range of, there are certain ranges given. Now, this for this calculation you have to, what we have to find out is for a circular orbit of this height, first you have, and it is a circular orbit, first you have to find out the velocity in the orbit, then velocity in the direction of the observer when it is rising from the horizon. So, if you know the velocity towards the direction, you can find out the Doppler shift and the original frequency, transmit frequency is known. So, the orbit radius, that is RS, is 1000 kilometer plus 6378 is 7378 kilometer. So, velocity is mu by RS root over, which comes out to be 7.35 kilometer per second. And when it is rising from the horizon, the VR that component velocity which is coming towards the observer is v, this v and cos of theta, and the cos of theta, since it is making a right angle triangle when it is rising, is equal to R e by R e plus h, that is R s, which is 6378 by 7378, which is equal to 0.6844. So, V r with this cos theta value and this V value comes out to be 6.36 kilometer per second. And Doppler shift we find out. So, Doppler shift is, let us call f d is the Doppler shift, is V r into f by c, which is V r is 6.36 kilometer, that is 10 to the power 3, and the frequency was 2.65 gigahertz, that is 10 to the power 9, divided by velocity of light, we assume 3 into 10 to the power 8 meters per second. This kilometer converted to meter. So, this comes out to be 56.18 kilohertz, and the option range which was given in C range, you can see plus 55 kilohertz to plus 60 kilohertz. There is a minus 55 kilohertz to minus 65 kilohertz also. So, where it will fall? Since it is rising, the component velocity will be positive towards this. So, this will be a positive value. So, therefore, it is option C is the correct option. Now, let us go to the assignment 12. This is the again orbit, but orbit velocity, incremental velocity check. That is, a satellite was launched from a satellite launch pad located at 13.7 degree north, 80.2 degree east, with this seems to be our Satish Dhawan Space Center coordinate, seems to be, with azimuth of 102 degree, and was launched into a parking orbit with a perigee of 250 kilometer and apogee at geo height. During the class, I said that there is a parking orbit I mentioned which is supposed to be circular, and I said this type of orbit we called GTO, geosynchronous transfer orbit. It is immaterial what name you give. It is a elliptical orbit that is coming, where the perigee height, this is perigee means perigee height is 250 kilometer, and apogee at geosynchronous height. So, you can find out the apogee distance. So, apogee and perigee distances are known. So, let us try to solve this problem. There are two parts. One is elliptical GTO orbit, but it is launched from a launch pad which is away from equator. So, it will have certain inclination. That inclination velocity also has to be corrected to bring it to the GEO orbit, geostationary orbit, which is inclination is supposed to be 0, and there are options given. So, two part of the calculation. So, first part is what is the distance at apogee, or let us say what are the things given, GTO or the parking orbit, perigee is given, which is 250 kilometer, is obviously a height which is given, plus 6378 we have to take, and then the for GEO orbit, GEO The time period is a sidereal day is 86164 second. So, the radius of the GEO circular orbit R A, because the apogee it mentioned that apogee at GEO height. So, R A we calculate. So, R A will be T square mu by 4 pi square to the power 1/3 will come out to be 42164.12 kilometer. Now, for finding the velocity at apogee, we have to find out the semi major axis. So, semi major axis A is 42164.12 and this perigee distance 250 plus 6378 this divided by 2, which comes out to be 24396.08 kilometer. And then the velocity at apogee, that is velocity at apogee is mu 2 by R A minus 1 by A, this is V A square. So, V A from this value of R A and A value already you have got and mu is known, V A comes out to be 1.602 kilometer per second, right. And the velocity of a GEO, which is a circular orbit, which is mu by A to the power half, and by using this value of mu and this A which is R A in this case is equal to 3.074. I said A, it is actually R A, let us call it R A, no confusion. So, that is kilometer per second. So, now we have got a GEO velocity and we have a apogee velocity of elliptical orbit which are different. Now, one thing is it is a inclined orbit that is to be corrected. So, we will find out what is the inclination. To find out the inclination based on the azimuth and the latitude of the station from where it is launched, the launch azimuth was given as A is equal to 102 degree and launch latitude L is given as 13.7 degree. And if I is the inclination of the orbit, I is the inclination, then I is equal to cos inverse, this was explained in the class, sine of A into cos of L, which if you put this A and L value and sine and cos, if you take it comes out to be 18.14, or you can make it cos I also, cos I will be 0.95. Now, these two velocities are at two different vectors at having a angle between them, that is V A and V itself. So, the delta V I is V square plus V A square minus 2 V into V A into cos I and square root of that, which if you put the V A value and the V value, which is a GEO orbit velocity, this is the apogee velocity, and cos I we have found out. If you put that, it will come out to be 1.63 kilometer per second. And let us look at the options. The first option itself is 1.63 kilometer per second, others are much higher than that, and one says none of this. So, the answer will be option A, that is the correct answer. Now, we go back to the assignment number we missed somewhere, that is question number 6, and the correct option is supposed to be B. I think I worked out, yeah, if you recollect, we calculated eccentricity as 0.48 and the semi major axis as 31400. So, the option B is the correct option. So, this is option B is the correct option. It is just calculation, you do these calculations and you will get it fine. So, with this I tried to give some solutions to the which are simply using some calculators and using some formulas, but if you look at all these problems, the main thing is the terminology, like I said, orbital height. So, in that case, in our all calculation from the center of the earth to the center of the satellite, that distance is used for whether it is elliptical orbit or circular orbit. So, radius of the earth we have to take and assume earth as a sphere, radius of the earth and then height. Other things are mainly understanding of whether at apogee the velocity is low or perigee velocity is high, those are from the Kepler's law that is coming. And there was only one problem on the Doppler, that is also easy and simple calculation given in the Pratt's book, the same problem is given in the Pratt. So, thank you very much for listening to this, and I hope you will be able to solve many more problems, similar problems which are ellipse related and a little understanding of the basic laws. Thank you.